In this lecture, we are going to study collision. We learned much about atomic, nuclear, and elementary particles experimentally by observing collisions between them. On a larger scale, we can better interpret such things as the properties of gases in terms of particle collisions. In this section, we apply the principle of conservation of energy and momentum to the collisions of particles. In a collision, a relatively large force acts on each colliding particle for a relatively short time. The basic idea of a collision is that the motion of the colliding particles, or of at least one of them, changes rather abruptly, and that we can make a relatively clean separation of times that are before the collision and those that are after the collision. When a bat strikes a baseball, for example, the beginning and the end of the collision can be determined fairly precisely. The bat is in contact with the ball for an interval that is quite short in comparison to the time during which we are watching the ball. During the collision, the bat exerts a large force on the ball. This force varies with time in a complex way that we can measure only with difficulty. Both the ball and the bat are deformed during the collision. Forces that act for a time that is short compared to the time of observation of the system are called impulsive forces. If we consider two particles, say one particle, it has mass m1, and another particle, it has mass m2. Okay, the particle with mass m1, let us suppose that the linear momentum is p1, and the particle with mass 2 is, let us suppose that its momentum is p2. So the total momentum of the system p2. Now, if we consider collision between them, then there will be a change in linear momentum of the system consisting these two particles. So change in linear momentum is delta p1 plus delta p2. And if we consider that these two particles actually is an isolated system, the total momentum must be conserved. If there are no external forces, the total momentum of the system is not changed by the collision. The impulsive forces acting during the collision are internal forces which have no effect on the total momentum of the system. If only internal forces act during the collision, and no external forces act then means change of momentum of particle 1 is equal to, but in the opposite direction of the particle 1. So we can say that during collisions, linear momentum is a conserved quantity. Okay, we shall study elastic and inelastic collisions. Collisions are usually classified according to whether or not kinetic energy is conserved in the collision. When kinetic energy is conserved, the collision is said to be elastic. Otherwise, the collision is inelastic. Collisions between atomic, nuclear, and particles with fundamental in nature are sometimes elastic. These are in fact the only truly elastic collisions known. Collisions between gross bodies are always inelastic to some extent. We can often treat such collisions as approximately elastic collisions. When two bodies stick together after collision, the collision is said to be completely inelastic. For example, the collision between a bullet and its target is completely inelastic when the bullet remains embedded in the target. Even if the forces of collision are not known, we can find the motions of the particles after collision from the motions before collision, provided the collision is completely inelastic, or if the collision is elastic, provided the collision is a one-dimensional one. For a one-dimensional collision, the relative motion after collision is along the same line as the relative motion before collision. Okay. For elastic collision, kinetic energy is conserved. Okay, now we shall consider elastic collisions of two particles in one dimension. So if we know the masses of the two particles and the velocities of the particles before collisions, and we will try to find the velocities of the particles after collision, and we shall use the conservation of linear momentum and conservation of kinetic energy for this elastic collision. Okay, so let us suppose that we have two particles with mass m1, velocity v1I, and another particle mass m2 and velocity is v2I. Okay, and after collision, particle 1, say velocity is v1F, and particle with mass 2 will have velocity v2F. Before collision, and is after collision. Okay, so this is one dimensional. The particles are moving along this straight line. Now we have two conservation relations. Okay, now as I mentioned that we know the masses of the two particles m1 and m2, and also we know the velocities of the two particles v1I and v2I. We are now going to find the velocities of the particle m1 and m2 after collision. Conservation relations. Momentum, actually this is linear momentum conservation. So the linear momentum before collision is m1 v1I plus m2 v2I is equal to after linear momentum of the system after collision. Our system consists of two particles, particle of mass 1 and particle of mass 2. Okay, now mean linear momentum after collision is m1 v1F and m2 v2. Okay, we have kinetic energy. As we said that during elastic collision, the kinetic energy will be conserved. So kinetic energy conservation. So is half m1 v1I v1I square plus half m2 v2I square, and after collision half m1 v1F square plus half m2 v2F. So let us suppose this is equation 2. Now equation 1 can be written as so we bring this one on the left side, this one on the left side, so is this is m1, so is taking common m1, so it will be v1I minus v1F, and taking this term on the right side, let us suppose this is 3. Similarly, equation 2 can be written as, bring this one on the left side and this one on the right side. let us say this is equation 4. Okay, now if we divide equation 4 by equation 3, so we will left with this. Now we want to find first V1F and then V2F. So from this V1 okay, let us say this is V2F equal to V1I plus V1F minus V2I. I'm putting this into equation 3. If we substitute this into equation 3, then after some algebra you will see that you will have V1F equal to M1 minus M2 divided by M1 plus M2 V1I plus twice M2 divided by M1 plus M2 V2I. Similarly, from 5, okay, this is the final velocity of particle 1 after collision. 5 can also be written as V1F equal to V2F plus V2I minus this one, take this side, so V1I. And putting this into equation 3, gives, in a similar way as we did previously, we will finally get V2F equal to twice M1 divided by M1 plus M2 V1I, and here M2 minus M1 plus M2 V2I. Okay, you should try at home to find these two expressions. You see, the right hand sides of equation 6 and 7 are known, and so the left side we can easily find out. Okay, next we shall study few cases of this collision, one-dimensional collision, elastic collision. Few special cases. case A, if we consider mass m1 is equal to m2. Okay, so if we have m1 equal to m2, if the masses are equal, then we see from equation 6 that when m1 equal to m2, so this term, first term, will disappear, and here this 2m2 and m1 equal to m2, so 2m2 cancel out, so 1f v1f will be equal to v2i. v1f will be equal to v2i, and from equation 7 we see that this when m1 equal to m2, so the second term on the right hand side will disappear, and from the first term on the right hand side, so this will be 2m1 and the denominator will be cancelled out, so v2f equal to will be v1i. Now what we see in this special case, that after collisions simply the velocity will be exchanged. That means you see the final velocity of particle 1 will be equal to the initial velocity of particle 2, and final velocity of particle 2 will be equal to the initial velocity of particle 1. Okay, next we consider case B. Say initially the particle 2 is stationary, that v2i is 0. Okay. Previously हम कैसे masses of the two particles same, and here in case B, particle 2 is stationary before collisions. So if the particle 2 is stationary, then this term will disappear because this is 0. So we will be left with only this, and here this term will be 0. So v2f will be this term only. So we will have this one will be 2m1 okay, so we'll have these two. Okay, now case C. M1 equal to M2 and V2I equal to 0. The masses of the two particles are same, and particle 2 is stationary before collision. Now you see in case B we have when the particle 2 is stationary, so we had these expressions for the final velocities of particle 1 and particle 2. Now here if we put m1 equal to m2, then we'll get this case C. So if we put m1 equal to m2 here, where v2i is 0, so v1f will be 0 and v2f will be v1i. So is in the denominator will be twice m1. This one is equal to this one. So is v2f will be v1i. This is very interesting. You see, when both particles are with the same mass, m1 equal to m2, and particle 2 is stationary before collision, then after collision what happens? Particle 1 will stop, its velocity becomes 0, and particle 2 will have the velocity equal to the initial velocity of particle 1 before collision. Next we consider case D. M1 is very smaller than M2 and V2i equal to 0. That is, particle 1 is much lighter than particle 2, and particle 2 is stationary. From the previous equation 6 and 7, we find that V1f will be equal to minus V1i and V2f will be equal to 0. What we see from these, final velocities of particle 1 and particle 2, there is when a light particle collides with a very much more massive particle at rest, the velocity of the light particle is approximately reversed and the massive particle remains approximately at rest. For example, let us suppose that we drop a ball vertically downward onto a horizontal surface attached to the earth. This is in effect a collision between the ball and the earth. If the collision is elastic, the ball will rebound with a reversed velocity, you see, minus v1f equal to minus v1i, and will reach the same height from which it fell. Okay, now we have finally case E. Here we consider particle 1 is very massive. M1 is very greater than M2 and particle 2 is stationary. This particle 1 is much massive, heavier, and particle 2 and particle 2 is stationary. Okay, in this case, we find from those previous equations that V1F will be equal to approximately V1I, and V2F will be equal to twice V1I. This means that the velocity of the massive incident particle is virtually unchanged by the collision with the light stationary particle, but that the light particle rebounds with approximately twice the velocity of the heavy incident particle. You see the twice, two times. But that the light particle rebounds with approximately twice the velocity of the heavy incident particle. The motion of a bowling ball is hardly affected by collision with an inflated beach ball of the same size, but the beach ball bounces away quickly. Now, there are some lot of practical applications of these, elastic collisions in one dimension or in other dimension. Neutrons, for example, neutrons produced in a nuclear reactor from the fission of uranium atoms move very fast and must be slowed down if they are to produce more fissions. Assuming that they make elastic collisions with the nuclei at rest, what material should be picked to moderate the neutrons in the reactor? This is a question. We can answer this question from the consideration just discussed. If the stationary targets were massive nuclei like lead, the neutrons would simply bounce back with practically the same speed they had initially. If the stationary targets were very much lighter than the neutrons, like electrons, the neutrons would move on with practically the same velocity they had initially. However, if the stationary targets are particles of nearly the same mass, the neutrons will be brought almost to rest in a collision with them. Hence, hydrogen, whose nucleus, which is the proton, has nearly the same mass as a neutron, should be most effective. Other considerations affect the choice of a moderator for neutrons, but momentum and energy consideration alone limit the choice to the lighter elements. Okay, this is for today. We now stop here. In the next lecture, we study the inelastic collision, and in particular, the ballistic pendulum and collisions in 2 and 3 dimensions.